Hello there and welcome to the iRevise supplementary series for GCSE Physics. This is our second of two videos on the waves topic in which we look at basic properties, electromagnetic spectrum, Snell's law, total internal reflection, that sort of thing. And we are going to tailor this video exclusively to WJEC content for seismic waves, which is a big part of their paper 3. We'll also take a look at the ubiquitous question of the fiber optics versus satellite communication. And we'll also take a look at some analog and digital signals questions from the Edexcel unit. Without further ado, let's get on with things. Starting things off, we've got analog digital signals question. This is from GCSE Edexcel. This is January 2013, paper 2. So yeah, 1901, Marconi receives the first radio signal across the Atlantic Ocean. The signal was the letter S in Morse code and just sent over and over. Morse code is 3 quick dots. You can see dot, 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 right? Okay. The graph shows the strength of the signal. The signal is either being sent, it's either on or off. So you see it's a digital signal. The graph shows digital. What is meant by digital? So digital has either values of 1 or 0, or high or low, or on or off, and that's it. There's no in between. It's either on or off. Explain it something like that. It's just two ways the signal could be made to carry more information. Well, I am not an expert on this topic, but I would imagine that if you have a graph here, and this is the time in seconds, if you were to speed things up and send more pulses per second, you could do that. So if you increase the frequency, I would say would be one of them. I'll have to take a look at the mark scheme on what they're looking for the other one. I don't know off the top of my head. Right, so they give you the radio frequency here, and they give you the wavelength. State the linking equation. Here's our wave equation. Calculate the speed of the radio waves. Okay, so 820 kilohertz, so that's times 10 to the 3 times, yeah, radio waves are fairly large, aren't they? 366 meters for, that's almost a kilometer, that's it's a third of a kilometer for a radio wave. I get here 300, well, I was going to say megameters, but we don't really use those units. We'll say it's 3.0 times 10 to the power of 8. Well, would you look at that? It's the speed of light.
George, you know, I was wondering, like if you were traveling through outer space, I mean, like you're going real fast, like the speed of light, you know, and all of a sudden you start screaming, ah, ah! You think that your brain would blow up?
Guys, I'm trying to work. Do you mind?
Okay. And some people do not believe that he received this frequency. Some think that the frequency was higher. If these people are correct, what wavelength did he receive? Well, wavelength is velocity divided by frequency. So speed of light divided by 1640 times 10 to the 3. And if you do that, you get, I'm going to round it up, 183 meters, so a bit shorter there. Let's check the answers. The signal has 2 values and only 2 values. So you can say it's binary, you can say it's on or off, 1 or 0, but then you need to mention it's only those 2. Okay, which is what binary means. And let's see, any 2 of these ideas. So it can increase the frequency is what I said. Okay, send more Morse code more quickly. What else have they got? They've got regeneration, using increased bandwidth, additional signal level. So you can have 1, 0, or 2. See, because that can be digital. A digital doesn't need to be binary. In this case, our digital signal was binary, but a digital signal doesn't need to be binary. You could have additional signal level. You could have 0, 1, and 2. You could have done that. Multiplexing using more than one channel. Okay, so this is getting, you know, there's some other things you could say here. Yeah, so there's our wave equation. There's our calculation. And there we got our calculation there as well. Okay, this is from January 2015, paper 1. Which letter represents the angle of refraction? It will be D. It is measured from the normal. Explain how the student can use the glass block to find an accurate value of refractive index. So you've probably done this practical in class. Okay, so you can, I'll just I'm not going to write it all below, but you basically you could have a line. Usually there's a line set up. You have a normal drawing. You set the block up. You trace an outline of the block. You have an angle of incidence there. Okay, what we will do is we will worry about it coming out, and so you can either trace the light beam coming out, or there's the pin method where you put 2 pins there, and then you can meet up the lines later. The idea would be that you would have a number of angles of refraction for different angles of incidence. How do you get different angles of incidence in the block? Well, you would adjust the angle of incidence here, which would cause a different refracted angle, which means a different angle of incidence on the exterior surface when you're emerging from the brick. And once you've done that, then you make a table, you do a little chart, you could plot your points, you could do an average of things. I would say something along those lines is what they're looking for. Just explain that experiment. Okay, so yeah, D was correct for our experiment here. Mention of the ray box or the pins, sure. Okay, just mention that you've used a protractor to measure the angles. Okay, varying angles of incidence to get a range of values. I had alluded to that. You would want to specifically state that. You, of course, can plot a graph of sin I versus sin R, and the gradient will be the refractive index. So mention, here's the equation. State you're going to plot that graph. You can say that you, and then, or just do some calculations. You can say the gradient of the graph is the refractive index. Okay, and then just talk about some precautions like don't burn yourself on the light bulb and this kind of stuff. Improvement to the basic method, greater range of data, more intervals, more intermediate measurements, that sort of thing. Okay, you could talk about a lot of other things, using a ruler to link your pins or the dots you made to trace. Make sure it's a thin beam, make sure it's monochromatic, sharp pencil, all of these types of things. It's a very straightforward experiment. This should be an easy question for you, hopefully. Moving on, another E&M question. It might not make the cut, but this is from January 2015, paper 2. Some pulsars emit radio waves, some emit X-rays. State properties of waves. That's the same. We could say they are transverse waves. We could say same speed in a vacuum. We could say, and that in a vacuum part is very important because they will be different in different media. What else could we say? They transmit energy. You could say they travel at the speed of light, that sort of thing. What are 2 properties that are different? Okay, so you could say X-rays have shorter wavelengths. The X-rays have higher frequency, something to that effect. Okay, or energy, I guess. Let's see here. We've got now again. So here's a little graph. This is like a communications type deal where they like to do analog digital graphs and that sort of thing. So explain how the graph shows the signal is not digital. Well, you can see that it goes up and down, up and down. A digital graph would be either one level or another level, and it would have discontinuities. And so we could just say graph it's continuous, if we can use those terms. We can say has a range of values, and it's not simply one level or the other. Okay, something about that I think should be okay. We'll see what the mark scheme says. Use the graph to estimate the average time between each pulse. Okay, well, I mean, this is a nice one right here. 3 to this one here. That looks to me like about a 4.3 minus 3. So one. I'm going to say 1.3. And I think if you went from here, which was 0.4 to 1.7, yeah, it's a 1.3, I would say. So just show that you've done some work on the graph. I'm sure you get it. Calculate the frequency of the pulses in the signal. I know we've just said it's 1 per every 1.3. I'm wondering if you might do like an average where you go from here to here. You might say, hey, I've got 5 and 6. 5 and 6 is going to be a 0.833. If we do 1 over 1.3, that's a 0.76. Let's look at the mark scheme. So what were some similarities? Same speed, yes. in a vacuum, of course. They are transverse waves. Oh, electromagnetic waves. Yeah, good. Any general wave property means they will reflect, they will refract, they will diffract. They transfer energy, I said. Okay, good. Right. What's different about them? Good. Frequency, wavelength, and energy. Okay, so you got 2 to choose from there. Let's see here. There are more than just 2 values. Why is it not digital? Well, we saw it. We saw not all peaks are the same height. Oh, I missed that, but yeah. It's just not just 1 and 0. Fine. Ignore. Don't say. It's got. Well, I said it was continuous, so it's got shapes. It's got slopes. It moves up and down. Okay. It doesn't jump. Okay. Right. More than one gap measured, averaging seen. That's so you get it 1.15 or 1.35. Well, I didn't do an average when I found out the 1.3.
Idiot! God, so stupid. What a dumb question.
I only went from 1 to 3, and then I was thinking about doing the averaging for the next question, which is maybe a bit silly.
What are you?
An idiot sandwich.
What we should have done is said, hey, look, this is 0.3, and we're going to go 1, 2, 3, 4. So there's 4, and this goes all the way to 0.5. So there's 4 in 5.4, and 4 divided by 5.4. 2 marks for bald answers. 1 mark, this or this, and then so you can get some pretty bizarre numbers there, I suppose. Okay, and then we were overthinking it, or at least I was overthinking it. You just take your answer and do the reciprocal. That's all it is. The frequency is 1 over the. So you don't need to do any averaging there. The averaging should be done when you measure the initial bit. Okay, this is what we had. We had 1 over 1.3. So there we go. This is paper 1, January 2016. Again, we just seen the similarities one, so we'll just skip that. We know what it is, and what's the damage they can cause. Ultraviolet can cause some skin cancer. Infrared will cause burns to tissue. Ultraviolet can cause cancer in long-term dosage, that kind of stuff. What color has the longest wavelength? Red. Right, very straightforward. Yeah, it's red. Ultraviolet can do damage to cells. Ooh, blindness. Yes, Galileo lost his sight staring into the sun with a telescope. You don't want to do that. So blindness, okay, or damage to surface cells, skin cells, and skin burns, okay. And the similarities, yeah, same thing. Transverse, travel through a vacuum at the same speed, don't need a medium. They're E&M waves, transfer energy, they carry information, all that kind of stuff. Okay, so the same paper here has a question 6 here, talking a bit about reflection. Which of these shows reflection from a mirror? That's what we want, because we're going to have angle of incidence equals angle of reflection. Here we've got a diagram. Draw the normal for this refraction. So get a protractor, get a ruler, try to draw a nice straight line. Make sure it's 90 degrees. I'm not the best there, but make sure you've got that. And if you draw that little square, if your diagram's not that good. On the diagram, mark the angle of refraction. This will be the angle of refraction, and measure the angle of refraction. Measure. Bring a protractor. If you don't have one, get one. State the relationship between the refractive index, the angle of incidence, and the angle of refraction. So this is the one that we saw in the other question. Okay. Calculate the refractive index of the glass. That's right. So they would have told us up above here, angle of incidence is 43. So we'll just plug in our numbers, right? Sine 43 over sine of whatever we measured up there, and we'll get our number there. Let's move on. You know how to do that. Okay, this question here on fiber optics. What is the name given to this effect? This is total internal reflection, and I believe TIR might even get you the mark, but don't quote me on that just yet. Explain what's happening to light in the glass fiber. Let's just say as the inside medium is more dense than the outside, and it won't be just air. There'll be usually there's another it's called cladding, like another material that's around it, but whatever. It's more dense than that material, whether it's that or the air. It's more dense than the outside medium, and hitting above the critical angle, it is totally internally reflecting. Like, totally, dude.
Totally.
Right. D, we said normal drawn, yes. The angle marked correctly, yes. Correct angle marked to the normal. Draw the normal. Mark the angle of refraction. Well, that's the angle of refraction. Measure the angle. Correct angle marked. Yeah, we marked it. And then correct angle chosen. Well, within 3... I guess you have to measure it. I'm not sure what they mean by chosen. Anyways, that's our formula. And we had, yeah, that's glass. That's 1.5. We'd shown that we would have had that. Total internal reflection. You just write TIR if you like. That's fine. What's going to happen? The light reflects inside of the surface fiber with an angle greater than the critical angle, and this is because light travels slower in glass. This is an unfortunate example of reading too much into the question. So we were talking about total internal reflection in part I, and then so for double I just assumed, okay, explain what's happening to the light in the glass fiber. So I thought, explain the process of total internal reflection. And it seems they're going for something much more basic. What's happening to the light in the glass fiber? You've got to answer quite literally what they're asking. So what's happening to the light? So that's why they've gone for that in their mark scheme. Moving on to the WJEC papers, this is January 2006, this is paper 1. Just fill in the E&M spectrum. I mean, these are very straightforward, right? So this is UV and this is micro. Maybe write the whole words in. Underlining the correct phase, visible light travels same speed as radio waves. The frequency of visible light is lower than the X-rays and wavelength is shorter than radio waves. Right, these are nice little diagrams. Distance between point and point is equal to 1 wavelength. Well, I would say A and D. I would also accept B and F, and that's about it for what these were labeled. Or, I mean, B and G, either way. But probably F is better because it's up top. The distance between between point G and F is equal to the amplitude, I would say. Okay, mark scheme real quick. Ultraviolet microwave, same as lower, shorter. Yes, we said BF or AE, FG. And that was a higher tier question, so we'll move on. Okay, and this is June 2017, paper 1. We've got a graphing question. Maybe you did this experiment in class. Okay, so describe how the speed of the water changes with the depth of the water. There's 2 points here. I would say as the depth increases, as depth increases, speed increases, but at a decreasing rate. Okay, part B, we've got a wave pool where it's deeper in one area. What are they asking? State the speed of the waterways between B and C. Okay, I guess we're going to have to go back to the graph or the table. So between B and C, it's at 2.5. There was no 2.5 on the table, so we'll have to go off the graph. And I think, to me, it looks like 3.3. So I'll say 3.3. We use this equation. The time taken for the waves. Okay, so they gave it to you. That's nice. So 6 divided by 3.3. It's going to be a little less than 2. 1.818181. Let's have a look in a moment. And as the waves travel along the surface A to D, their frequency remains constant. Describe. It's a written. Oh boy, here we go. Describe how the wave changes as it travels between these 2 points. A to D. Okay. Use information from your graph. Use the equation. Do not calculate times as part of your answer. Okay. Well, I think if we break it up between A to B, B to C, C to D, we know that here it's going to travel faster because it's deeper. Okay, and then it's going to move back, and it's the same height, so I would imagine back to being the same speed. I want to do this fairly quickly. I would suggest breaking it down between A to B, B to C, C to D. They want you to calculate, or they want you to use this wave equation. So describe how the wave changes. Okay, so here it's at a speed. Here we can say speeds up because it's deeper. And I suppose we could do... They give you the frequency. I suppose we could do some calculations. Oh, we can talk about what's going on with the wavelength because frequency is constant. It means that if the wave speed is going up, the wavelength will go up. So this will have a larger wavelength. In this case, the wavelength will go back down to normal or the previous results, or the previous values. Let's just take a look at what they'd be looking for here. Indicative content between A and B, the depth of 1.5. So give as many. You know what? We could do a little more detail here, can't we? We can say, hey, at a depth of 1.5 meters, it was 2.7, wasn't it? So at 1.5 meters, the speed was 2.7 meters per second. Okay, and we would say here, back to 1.5 meter depth, therefore 2.7 meters per second. All right, anything else? 2.5. So we had said 2.5 is going to be at 2.5 meter depth, 3.3 meters per second. And in order to go faster along that spot, that wavelength needs to be larger because it's traveling at the same frequency. Let's check out the indicative content. So, yeah, nice. At a depth of 1.5, this is the wave speed. That's from the graph. Between B and C, it becomes 3.3. That's an error carried forward from your previous answer. And then it reverts. Nice. Reverts back to 2.7. That's fine. The wavelength. Okay, so we didn't calculate any wavelengths. I missed that. It did say to use this equation. Didn't calculate the wavelength. I got distracted with telling you about some other things. So what could the wavelength be? Well, 3.3 divided by 0.6 hertz. So over here, we have got a wavelength of 5.5 meters. And in these situations at 1.5, the wavelength from A to B and C to D is going to be something along the lines of 2.7 divided by 0.6, which gives us 4.5 meters. So it changes by a meter. Okay, so there we go. There we go. That amplitude not affected. Okay. So, I mean, really, it's just a bunch of calculations. If you are not really strong on QWC questions, QER questions, you don't like the written stuff, you should really be thankful when you get a question like this. It's telling you to do some calculations. You break it down into the 3 sections of the graph, use information from your graph. You're reading numbers off the graph is all you're doing. Oh, 2.5, 2.7, 1.5, you know, that's all you're doing is reading stuff off the graph and then calculating something else. A very, very lucky QER question to get. Okay, another question about the water waves. This is more of an experimental type one here. All right, and WJEC fans, this is what we've been waiting for. I mentioned this in the astronomy video also, but I know that they are big in the waves unit to compare a geosynchronous satellite orbit with a fiber optic link. Okay, this is from June 2012, paper 1. Right, calculate the time it takes for the signal to travel if the fiber cable is this long. So time is distance divided by velocity, but we are not putting in c for speed of light. Okay, the velocity is not speed of light. It is going to be frequency times wavelength, because here's the frequency and there's the wavelength. Okay, your velocity, it's 4 times 10 to the 14 times 5 times 10 to the negative 5. Okay, because the velocity of that radiation in the glass will be slower than the speed of light. Speed of light is that c is in a vacuum. We're not in a vacuum. Okay. So, and then here's the distance. All right, so that's 450 kilometers. That seems a bit short, but I guess we'll go with it. Watch on your division here. Get these in the brackets. Maybe multiply that first. Please be careful when you type things in. Some people use the wrong buttons, and your calculator thinks you're dividing only by 4, and then you're multiplying by the rest. Okay, you're going to be actually dividing by each of these, or you put it in a bracket. If you use your exponent button, then you should be okay. But you're going to have to say divide by 4 times 10 to the 14 and divide by 5 times 10 to the negative 7 on your calculator. If you don't put the bracket there, your calculator might not like that. Okay? Yeah, and I think I tried this earlier and I made a mistake. I think that's probably the problem, because I got a much better answer now. So it's about 2.25 times 10 to the negative 3, so 2.25 milliseconds. Okay, moving on. I don't have these equation sheets in front of me, but I'm sure we can figure it out. Find the approximate height of this of the geosynchronous satellite if the time delay is this and the speed is this. Okay, so we want the height. Let's just look at what's going on. We're going to send a signal up, and it's going to come back down. We're not worried about the angles too much. We're going to have double this distance, aren't we? So whatever our distance is, velocity times time, again, it's that echo thing. We're going to divide by 2, aren't we? Okay. So I think we plug in the numbers here. The distance that I get is 36 million, or 3.6 times 10 to the 7 meters. That's the height above Earth. How are we doing so far? Correct time, correct height, and I think we've got the marks. Take a pause to see how they are being awarded. Let's move on. Explain why the satellite must be in a geosynchronous orbit. It needs to be above the 2 cities. Needs to be above the cities. If it's somewhere else, that's not going to work. Okay, it needs to be right above there. Otherwise, it won't be above, and we won't be able to use it. I'm wondering what they need for 2 marks for that. Give one advantage of sending signals by a fiber optic link instead of using geosynchronous satellite. Fiber optic link, less likely to be intercepted, I suppose. Probably cheaper to run the cable across the English Channel than to launch a satellite. What's the time delay? 2.4 seconds for the satellite, and milliseconds, absolute milliseconds for Faraday. So I would say, let's go back. This is what they want. Shorter delay. It's milliseconds. It's 1,000 times faster. Okay, much less time taken, faster, not affected by weather. Good call. Okay, why does it need to be geosynchronous? It needs to be above a fixed point on Earth, so satellite dishes do not have to be moved. That's the bit that I was forgetting. Yes, okay, so I said it needs to be above the 2 cities. That's fine, but if you think about all your sky satellite dishes and all these things, we aim them in one direction, and that's that. We don't want them to have to move around and track and trace when you've got the satellite moving around, okay? So, again, second mark must be linked to the first. So, I said above the cities. I think that's the same as saying a fixed point, but so the satellite dishes don't have to be moved. Okay, that's a tricky one, and in this digital age, I don't know how many people might think of that, so make sure you remember that one. Okay, and now the moment we've been waiting for. I've got a bunch of paper 3s here from WJEC. They're pretty big on these seismic wave questions. Just real quick before we do that, we've got this question here. Typical transverse versus longitudinal waves, know the differences, that type thing. So explain the difference between the 2 different waves. Yeah. And use these phrases. I mean, they're telling you what to do for 3 marks. It's pretty straightforward. So we can say that the particles in transverse wave, they vibrate up and down while the direction of the wave is to the right. So we can say that for transverse waves, the particles are vibrating at right angles to the direction of travel. And for longitudinal waves, we know that the compressions and rarefactions are parallel to the direction of travel, something like that. And this part here, do a little diagram. So they want you to complete the diagram to show the path of the reflected waves. Okay, so 5 marks. Grab your ruler and equally space and make sure that you've got these lines coming out equal spacings. Okay. And it should probably take you to the reflection, okay, well, at least to the normal there. Now it's 45 degrees. It's going to reflect. You're going to have your protractor. Maybe I'll draw a different color line here. Your protractor should help you measure a line coming out, and it should be, again, 45-degree angle for the reflection. Okay, and what should that mean for the reflected wave fronts? I'll use a different color, but they should be the same width as the original, same separation, I mean, same wavelength as the original. It'd be something like that, I suppose. Okay? Okay, so we've got a question here from June 2013. The light's critical angle here is 42 for this material. It's going to enter at A, and then what's the name for this change of direction and Y? Okay, so it's refraction, it's refracting. And why does it refract? Well, we can say the wave, I don't know, we can say two things. We can say it slows down. We can say that the wave length decreases, but it's entering the wave slows down in a more dense medium, and maybe you should say a more optically dense medium, but we'll see. Okay, they want us to draw on here the correct ray. Well, you know it's going to hit at 70 degrees. That's above 42, so it's above the critical angle, and it looks to me like you're going to get a nice reflection out to E there. Give 2 reasons why. Okay, well, we're moving or going from the optically dense medium into the air, which is less optically dense. Write that out. And the angle of incidence is above the critical angle. Write that out in words. And let's take a look at the answers. So refraction, passing from a less to a more dense medium. Passing from a less to more dense medium. Oh, yeah, at A it was, yeah. Or the light slows down, yeah. E, we said, strikes at an angle greater than critical angle, yes. Directed from more to less dense medium, yep. And the angle of reflection is equal to angle of incidence. Oh, okay, yeah. So, because that's going to give us TIR. So I was explaining the TIR. Yeah, you could have just explained, hey, it's going to reflect. It's total internal reflection. So these angles need to be equal. So there's 3 things you could have said there to get the 2 marks. Okay, moving on to number 5 from the same paper. Here is the first of a few seismic questions we're going to look at.
Soundwave, dispatch Rumble.
Rumble, activate pile drivers.
Ready, Rumble? Ready to shake. Ready and quake.
Let's get ready to rumble!
I'm impressed.
So they're asking, so we got an earthquake at E, and we've got some waves which will be traveling along. What waves will be detected between B and C and between C and D? Okay, well, first of all, we need to maybe just recap about the difference between S and P waves. So if you take a look on BBC Bite Size for WJEC version, all right, S and P waves, okay? So P waves are longitudinal, they're fast moving, they can go through both liquids and solids, all right? S waves are transverse. You can remember the transverse S waves, all right? They are slower than P waves, and they only travel through solids. So 3 S's there for S waves: transverse, slower, and solids only. Okay, so if you can remember that, we'll go back in here and let's just see what's going on. So between B and C, so what waves would be coming through here? Well, we know that we've got a solid crust or mantle, and we've got a liquid core. So anything going through here, through both liquid and solid, I'm going to have to say are P waves. And then between C and D, and if we take a look at this diagram here, this wave, whatever it is, when it hits, it's refracting, and then it kind of refracts out and away. So, you know, I'm not sure what waves are going to come in and hit in here. So, because, you know, it's only going to be P waves coming out up to C, but I don't think there's going to be anything coming in between here, because either it comes just a bit through, or it's going to refract and kind of move out. So between C and D, I'm not sure. I'm going to guess none. Explain how the Earth's structure affects the path of the seismic wave that passes from E to A. Because this is solid, and it's going to go through a liquid, and then a solid core, and then through the liquid core, and then back through the solid mantle. So I'm not sure what they're looking for on this one here. It's just going to be going between both solid and liquid. It's going to be going between solid, liquid, solid, liquid, solid. It's alternating. How would they want you to answer that for 4 marks? So it's not a full-on written question. Okay, so what did we say here? It looks like P waves, yes, for the first part. Do not accept as a shadow for S waves, okay, because P waves can make it through. And then it says the answer is surface waves, right? Because there's 3 types of waves. You've got S waves that are transverse, solid, and slow. And then you've got your P waves, which are longitudinal, fast, and go through liquid and solid. And then you've got surface waves. So I guess we could have said surface waves. All right. But they're saying surface waves or none are detected. It's in the shadow of S and P waves. Okay. I hope that makes sense. All right. And then so for part B, yeah, it's just coming back to me now. It's been a few years, but in the mantle, the stiffness increases with depth. And so that means if there's a greater stiffness, you have an increase in wave speed. Okay? We talked about going from solid mantle to liquid core, and then liquid core to solid mantle on the other side. When you enter the core, the stiffness decreases. Yeah, which means the wave speed will decrease. So the stiffness increases, wave speed increases. If it decreases, the wave speed decreases. But they talk about density increasing here. When you enter the liquid core, the density increases. That seems a bit counterintuitive. But there's 4 points there. I hope that sounds familiar. Let's move on. Okay, another seismic wave question here. This is very typical. We've got an earthquake that occurred in China. They give you the time, the position of the seismic recordings are there, Tokyo, Hawaii, and Hong Kong. A trace produced by the Hong Kong station is shown below. Okay, remember P waves travel faster, so they're going to hit first, and then the S waves will come after. You can think of, well, this is probably why they're called this, P for primary and S for secondary. They're the second ones to come. Okay, and so they tell you the times here. Okay, they tell you how many second delay. All right. So, what's the question? Use the information to answer the following question, right? So there should be an equation. Calculate the speed of the P waves traveling from the epicenter to Hong Kong. Okay, right. Well, the speed's going to be the, I'm going to write it up here. You should do it down below, obviously, but you're going to have your distance here, and it looks like that would be the delay. So 1958 divided by 240. That's going to be about, let's just say 8.2. Okay, so you show your calculation here, obviously. Explain what similarities and differences you would expect between Hong Kong, Hawaii, and Tokyo trace stations. Okay, here's a little written answer. And they're telling you what to write about. Statement describing how the traces would be different. How would the traces be similar? And calculations showing how the greater distances affect parts of the traces. Okay, well, that's easy. So how would they all be similar? What would be similar about all 3 of these stations? Okay, I'm going to write it up here. I'm going to say the similarities are going to be that the P comes first, then the S waves. Yeah, there'll be a delay between the P and the S waves. Okay, what will the differences be? What will the differences be? The differences will be the further away, the greater the delay between the P and S. Okay, so the delay will increase for greater distances between. Yep. Anything else? And then we just do some calculations. Okay, we figured out the wave speed of the P wave here. Okay, scroll back up, showing how the greater distances affect parts of the traces. Okay, well, maybe that's okay. So this is for Hong Kong here, and this, you know, if we wanted to calculate the speed of the S wave, we could. Here's what you might do. You've got the speed of the P wave. You could use this information here, this distance, divide by a larger time, and you'll get the speed of the secondary wave. It's obviously going to be slower than the speed of the primary wave. And now that you've got the speed of the waves, and you've got the distances to Tokyo and the distances to Hawaii, what you might do is you could calculate the time for the P wave to Hawaii. You could calculate the time of the S wave to Hawaii. Okay, you would take the distance to Hawaii, and you'll divide by the velocity of the P wave, the velocity of the S wave. You'll get the time for the P wave and S wave to respectively hit Hawaii, and then you would subtract them, and you could calculate the time delay. So some calculations like that. This is a really nice QWC question for you, because it's telling you 3 things you can do. You put some, whenever you got some calculations in those questions, that just makes it really nice. Let's have a look. Right, so yeah, we got 8.2. Maybe I was a little overzealous on the units. I think, do not accept 8.15, but 8.16 rounded up. I guess they like 3 sig figs. Make sure you know what your exam board's looking for. Some indicative comment. Similarities, P and S waves will both arrive at Tokyo and Hawaii. Yeah, okay, that seems a little obvious. We said the P waves will arrive before the S waves. Okay, good. Okay, differences. The traces will start later than Hong Kong because they have further to travel. It'll take longer for the P waves to reach there, and there'll be a larger delay between the P and the S waves. And they've done some calculations here. So this was to Tokyo, and so they divided by the speed of the P wave that we had up earlier, and so their trace will start later. You could talk about when the trace starts, and then you've done the same thing for Hawaii calculation, error carried forward from your previous value up here, and again, quite a bit of a delay, and so Tokyo trace to have greater gap than Hong Kong between S and P waves. Hawaii trace will even longer gap. Yeah, that's kind of what we had said. So there you go. Some other calculations. What's the delay calculation? So it's kind of like I was just saying up above. Again, you take that speed of the wave. You take that time. Now this is the time it takes. This is the speed of the S wave now. Okay, and we had the speed of the P wave up above, and then what you can do, time. So take your answer, divide it on. It's just like what I said before, and so you could figure out the lag time. Okay, amplitude at Tokyo is less than this is something else. Yeah, the amplitude at Tokyo will be less than Hong Kong and still less at Hawaii. The amplitude of these waves will decrease as they travel along that distance. A very straightforward type of question here. So did you address the question? Did you do everything they wanted you to do? Did you use the terminology? And did you do those calculations that they wanted? This should be a fairly straightforward question to do. You should be really happy if you get something like that. Okay, moving on. This is June 2017. It's a paper 3. We've just done a question kind of like this, so I'm going to move along. We did one. Well, this one's a little bit different. This is from deep to shallow water. Okay, and it's not a reflection now. It's a refraction. So we know that. Okay, let's just analyze because they're going to ask us to draw, measure the wavelengths. Okay, so you measure these, complete the diagram. Right. So we know that the wave is faster in deeper water, and it goes into shallow water. It's going to go slower. So the wavelength is going to go lower. And when it's going slower, that's like moving into a more optically dense medium. It will slow the light down. If you do that trick with the lawnmower axle, go check out 10-Minute Physics to see what I mean there. Right, so we know that we want these wavelengths to be smaller. I'm just let's see, if we just were to change what the angle might be a little bit, and if I were to, let's say, bend these this way, try to keep them parallel, I think, do we see that those wavelengths are closer together? I think we see that. And, you know, direction of wave travel would be perpendicular to them. I would say that the angle of refraction is less than the angle of incidence. Yeah, compared to this angle of incidence. So I think we've done that correctly. Right? You wouldn't want to draw them the other way, because then they would be getting very close to being parallel to the normal. So that doesn't make sense. So this way, because of the change in angle and change in direction of path, the wavelengths are closer together. I think that's what we like. And so, yeah, measure that value off of there, and then there's the diagram. Let's have a look at the mark scheme. Right, so they say 1 point. Okay, remember we skipped this because we skipped the first part because it was similar to what we had seen before. You measure this and it's a 1.3 apparently. Okay, and then we've drawn at least with 3 wave fronts. Okay, all wave fronts bending downward. We did that, and they're all drawn parallel to one another and with a smaller wavelength, and I think we've done that. You cannot have the sec mark awarded unless the first mark has been awarded. All the wave fronts have to be in the same way, and we have at least 3. We drawn at least 3. Okay, suppose we could have done 1 there as well. Okay, good. Right, let's move on to part C here. Right, okay, yeah, they like the written answer questions for these seismic ones. So what are they going to ask us here? Use your diagram and your knowledge to describe about the properties of PS and surface waves. This is a very, very nice, straightforward, easy question for you to do. I think we can kind of just summarize what I told you before about the secondary waves. They have the 3 S's. They are secondary. They are slower. Okay. They are transverse, and they only travel through solids. Okay. Whereas P and S will travel through liquid and solid. They are longitudinal, and they are faster. We've already talked about this. Surface waves travel along the surface. Okay? Yeah, use the diagram. Yeah, we could say, hey, so, you know, the P waves will be the only ones to make it to the opposite side. And hey, this is like a question we've already seen. This is A, B, and this was C and D, I think. Was that it? And so between A and B, what did we see? We'd see P waves. Between B and C, we saw nothing. It was a shadow. This is very similar to what we've seen in some other questions. Right, so indicative comment, yeah, P waves are the fastest, okay? They go through solids and liquids, and they're longitudinal. S waves are transverse, and they cannot travel through liquids. They travel slower. And P and S refract as they pass through the Earth, because they'll go through the mantle, through the liquid core. They'll do some refraction. Surface waves do not travel through the Earth, but are only on the surface, as the name suggests. They are the most slowest of them, but they create the most damage. Maybe you remember that. And they can be both transverse and longitudinal. And I think that's it. That's all you really need to say. Just kind of break it down into your 3 sections. And we could have said a little more about surface, but we've got that now.
Now we know.
And knowing is half the battle.
G.I. Joe!
Maybe you need to revise that a bit, but there you go. Check your notes, and you should have it all. Use your terminology, use the grammar. And there's nothing wrong with you breaking it up into 3 little sections, but maybe write some don't just do this. Obviously, you need to write some sentences out. Okay. Okay, and this is a June 2016, and this is a lovely little QWC question here. First of all, before we get there, though, label the critical angle on the appropriate diagram. I would say the critical angle is here, C, because that's the angle at which the refracted ray becomes 90 degrees. All right. Now, this is a lovely little written response question here. They want you to describe the observations in the drawings as you see. There's 3 drawings, 2 marks each. Describe what happens to the light ray in each of the diagrams above. Explain why the light ray follows the path shown in each diagram. That's all you have to do. This is really straightforward. Now, before we get going, I might say something like, you could address the fact that the light is hitting at 0 degrees and is not refracting on the way into the glass. You could address that if you'd like. You don't need to, right? We could just talk about what's happening at diagram A, B, and C. Okay. Well, what's happening at A? We can see, light leaves the glass. A more optically dense medium, and it's therefore going to speed up on the way out. It's going to speed up on the way out, and therefore it is the ray is going to move away from the normal. Okay, and it's going to have an increasingly larger and then you can say it's going to have an increasingly larger angle of refraction as the angle of incidence gets larger and larger and larger, to the point where we reach at the critical angle. And you can say at the critical angle, I like to say theta c. You can just write c if you like. But at the critical angle, you probably would write this out. At the critical angle, the angle of refraction is equal to 90 degrees. It goes along the surface of the water. And then part C, beyond, when your angle is greater than the critical angle, then we have total internal reflection. And just explain what's happening there. It's refracted actually beyond it. It actually comes in and totally internally reflects. Okay, and you could talk about how there's a little bit of a reflection there, but you know, it's just a little bit. But as you get closer and closer to 90, more and more reflects. Once you get beyond 90, it completely reflects. If you take a look at the O Physics website, reflection and refraction in the light category, you can see here that if I change what the angle of incidence is, and if I make it larger and larger and larger, and you can see how they talk about the percent that is reflected and the percent that is transmitted. Yeah, there's always a bit that gets reflected, because this is why we can see off the surface of water, for example. Okay, this is why we can see the reflection off the glass. But a lot of it gets transmitted. But if that angle of incidence gets large enough, nothing happens. That's because we're going from the light into the more dense medium. But if I were to switch these around, okay, and now we're going from glass. Now we're going from glass into air. Now you can see here, same thing. There's still going to be a little bit reflected back, but more of it's transmitted. But as this angle of incidence gets larger and larger and larger, we reach a point where at 42, if I just move this up little by little, you can see it's slowly getting closer and closer. But once I hit 42, boom, it's completely reflected back. I don't even, I can get this here. If I go back to 41.8, they don't tell you the breakdown, but it's mostly along the surface there. Some will be reflected back. So it's a partial reflection. And that's why this is called total internal reflection, because once you hit 42 or larger, that angle, see, I'm making it larger, but now it's completely reflecting, and so these angles are the same. And so it's totally internally reflected. Okay? So that's the kind of stuff you want to play around with and study and explain. This is a really straightforward question. Let's look at the mark scheme and just, so the C is in the middle drawing. That's right, that's fine. Indicative content, when the angle is less than the critical angle, it's refracted away from the normal as it passes into the air. This happens when light travels faster than in glass, or the light traveling from into an optically less dense medium. This is what we said. The angle of incidence is equal to the critical angle. Then it just goes along that boundary. Okay, and then if it's greater, then it's going to total internal reflection. And it's only when you're going from a more dense into a less dense, and you're bigger than the critical angle. Man, if you can explain all that, that's an easy peasy 6 marks.
Totally.
And finally, there's a question here about the fiber optics, and so you could say, hey, we're going into glass, so I'm going to have to move towards the normal a little bit, but now I'm striking, and you say, hey, now I'm striking at a very large angle. That's going to be greater than the critical angle, so I know I'm going to reflect, and you know it's going to just keep propagating like this. So something along these lines. Okay, what would you get for the marks here? Okay, correct refraction towards the normal on the way in at A, and then just show a bunch of TIR, and the reflections have to obey the law of reflection there, I equals R. So just by I, you don't have to, but I mean, you know, make it look pretty good. I don't go in and measure it with a protractor, but I mean, some students are pretty poor drawers. So make sure you indicate that those are the equal. Okay, very straightforward, nice, easy 10 marks. Okay, and now I've got a foundation level paper 3 for the WJEC, and this is from June 2016 as well. And basically we've got this question here about a map of California. That's where the big one's going to hit, and part of it's going to fall into the ocean, they think. And there's an epicenter somewhere on the circumference of circle A. Okay, so there's a station in Santa Barbara, and there's a station at station B. Okay, and so this is how you would find this. This is a good question, epicenter stuff. Okay, let's see. I know I've seen some questions where you need another piece of paper to use this scale. Let's just see. Let's see. All right, let's just see what they want here. The P wave arriving at station B took 25 seconds to arrive from the epicenter. I've got an X there. Is the epicenter at the X? Took 25 seconds to arrive. The speed of the wave is 6. Okay, so we've got that. Use the equation to calculate the distance of B from the epicenter. So 6 kilometers per second times 25 seconds, that's 150 kilometers. Okay. One of the other possible positions of the epicenter is shown with, okay, X. So mark the other possible position. Okay. I think what you want to do is you might need to get a piece of paper, and you might need to get a scale, and you might need to say, hey, I'm gonna measure this 150 from the epicenter. Okay, and then what you'll do is you'll have your piece of paper here. Okay, and then you will rotate it. You'll try to get things to line up. So maybe this scale here that you measure and then put onto this map, maybe this distance here is 150. Okay, so where else could it be? So you're going to rotate that page out, and you should have something out over here somewhere, I would imagine. Okay, let me clear this up. I would imagine you'd get something this distance here, equidistant, so somewhere around here, I would guess. Okay, but that's you'll have to get a corner of a piece of paper, copy that scale, or use your ruler. Okay, but it might be a few number of millimeters, maybe just a piece of paper, a corner is good, might be useful. All right, we'll check the answer on that. And then the record of, okay, so this is station A, and you know that the S waves come after the P waves. Their secondary waves come after the primary waves. 20 seconds later. State why the S wave arrived later. They are slower. They travel slower. They are slower. Fill in the gaps. The S wave arrived at station A. Oh, and then they want you to do that calculation. It's 20 seconds later. So 20 seconds later than this, so 6 hours, 1 minute, and 42 seconds? Is that what they're looking for? Okay, so the mark scheme, yeah, 150, good, we got the 2 marks there. Yeah, that's what we had said, right? Circle should be crossed in the position of the X marked above. The circle should be... That's what we had said. This is a different map. But this X is really close to Pasadena. So... Well, Pasadena's here. So here's an X, and then that distance needs to be the same out there. So that's what I was saying, yeah. You get my trick. It should be on the N, A, or T of national. Yeah, but that's on that map. This doesn't... Oh, I see. It should be on the N, A, or T of national. Okay, well, that's what I'd said, right around there. Okay, so good. And yeah, there we go. 6 hours, 1 minute, 42 seconds. Good. And P waves travel faster than S. Very straightforward. It's a foundation, but these are good to practice to make sure while you're learning. All right, and here I've got a question from OCR. It's the 21st Century Science. Yeah, this is the modules 1, 2, and 3. It's the A181/02. It's from May 2013. So yeah, just a very basic question here. I can't write on the OCR scripts either. This is annoying. That you have to fill in this. Well, we know that the crust is solid. We know the mantle is solid. We know the outer core is liquid. I've always been taught that the inner core is solid, but because there's You know, this evidence, I have a funny feeling they're going to want cannot tell. Okay. The center of most earthquakes is deep underground. This is usually what happens is we've got a detector. When the P wave arrives, it moves up and down because it's a longitudinal wave. And when the S wave arrives, because it's transverse, it'll cause the ground to go side to side. So by using properties of waves, explain the different movement of the ground. Well, that's basically it. That's why. I think I've said that. The only other thing you could say is that P waves move parallel to the direction of propagation, and S waves move perpendicular to the direction of propagation. So just why S waves usually do more damage than P waves? Well, I would say because S waves are moving, the ground side to side. You get the buildings to sway, and if the buildings are really tall, they need to be designed in such a way that we're not breaking their structural integrity. That would be my guess. And P and S waves. P waves arrive first. Yeah, we know that because they travel faster. That's why they're the primary waves, and the S waves are the secondary waves. Calculate the time difference. Okay, so the distance is 30 kilometers. I think the P and the S had different speeds. P waves were faster, so I'm pretty sure that would have been the 4, the one that I saw. All right, so velocity is distance over time, so that means that time is distance over velocity. So, 30 over 6 is going to be 5 seconds, and 30 over 4, that's halfway between 28 and 32, so I'll say 7.5 seconds. So the time delay when you subtract the two should be 2.5 seconds. Let's take a look at the mark scheme. Yeah, solid, outer core, cannot tell, apparently, whatever you've learned in your syllabus. Longitudinal move up and down, transverse moves side to side. Oh, so either one of those, 1 mark. And a longitudinal, they move parallel. Okay, so added in the extra bit that I said that at the end, and the transverse, they move at right angles to the direction. Okay, so you have to either talk about longitudinal and how they move up and down and are parallel, the particles move parallel to the direction, or talk about transverse and how their particles move at right angles, and that's why it's side to side. Talk about one wave or the other. Buildings are less stable in side-to-side motion. Yeah, and they're really high, and you'll have problems. C. Yeah. So 2.5. I think we've done that. That's fine. Then on the same paper here, I've got a digital analog question. So let's get on with that. Original waves are produced by the band are analog. Yeah, the radio picks up a digital signal, and Rye hears So it's a recorded concert. He hears it as analog, obviously, because it's coming out of the radio. So how and why is the signal transmitted as digital rather than analog? So 2 things to talk about there. Let's go to the mark scheme and see. So analog signal varies continuously. That's what analog means. So you should right away talk about what the differences between the two. Digital signal only has 2 values. Okay, good. How does it get converted? Okay, analog signal gets converted to digital. You can digitize things. Okay, this is what happens all the time when you rip a CD on your computer. Okay, signal is encoded on a carrier wave. The radio wave is turned on and off. The signal and carrier have transmitted as electromagnetic wave. The receiver records digital and puts it back to an analog signal. Loudspeaker produces analog sound waves. Well, that's what speakers do. They move in and out, and they will be analog, and there is noise picked up in the transmission. Okay, right. Analog radio does get noise, whereas I guess the DAB.
You go like that. Yeah,
Yes,
I was looking that up. So that's a dab.
Yes.
All right, I know what a dab is. I'm so excited.
So it's like you're dancing, all of a sudden you just dab.
Okay. Dab. Okay.
The DAB, the digital radio stations don't get the static. Is what I was reading in a different question before. 2 values of signal are easily recognized amongst the noise. This is the advantages. This is why they transmitted it as digital. Okay, so you really only need, I would say, 2 of each of these. So talk about the difference between analog and digital. Give 2 of these from the description I've talked about, and then 2 of these from the advantages. Okay, so it's easily regenerated. It's easily picked up out of other signals. There's no noise. It's easily stored on computer. Yeah, okay. It's easily processed by computer. Yeah, maybe they're putting in some effect for this recorded concert to make it sound like a concert hall. They add some reverb. They do some other processing. Yeah, okay. Digital signals of higher quality because the information is received as the original. Okay. And there's more information that can be transmitted. Right, so if you've done this unit in your course, you would know that these are some of the advantages of digital, so I'd leave you to that. Okay, and I've got another OCR. This is a Gateway Science paper. This is modules 1, 2, and 3. This is a June 2015 higher tier. So this question is about how a CD player works, basically. Okay, you've got a laser and you've got a detector. You've got lands and pits. You would know that when you learnt this that when the information is digitized, it is then made into this CD, and the CD has these little different levels, and it's either high or low, a land or a pit. I guess a pit it would be high, and a land is low. And the laser goes through a transparent layer of plastic. The engraved aluminum, if you will, is in between 2 layers of plastic. All right, and they want to know the properties of the laser beam, how the information is stored, and how it is read from the disk. So there are the 3 things to talk about for 6 marks. I would say 2 marks for each. Properties of a laser beam. What do you know about laser beams? Laser beams are monochromatic light. Laser beams, we want everything here to be in phase, and so we have a term for this. With lasers, it's coherent light. That's how we have our CD players working, with coherent laser beams. All right, and that's maybe good for now. Yeah, I'd just say coherent and monochromatic. And yeah, so how is it stored and how is it read? Well, I've already kind of talked about a little bit about that. And then how is it read? Well, we kind of already got into that a little bit. The laser goes in. It's going to reflect and then bounce back. There's a detector, and the time difference is either going to be a longer time difference for a pit or a lower one for a land. And so what happens is you get a signal, which is now, you're reading that same digital signal, and then it can be converted into analog in the speaker. Let's take a look at the mark scheme real quick. Okay, so nature of the laser beam, either you say the beam is coherent, which means everything about what they're going to say, or you say it's in phase and has the same frequency. What a coherent laser beam means is that it is in phase and has the same frequency. Okay, that's basically all you need to say about the laser, and it's actually really not that difficult here. You could just say we can digitize the music. It's stored in the bumps and the pits. Okay, and it's just reflected off, and then it's collected by the receiver. I don't think they have anything else there. That's really all you need to say. So hopefully you understand how that works, and you can explain with good English grammar, syntax, spelling how to do that question. Well, that's not too bad. Okay, and then the next question is a number 4 here. It's about S&P waves again. So again, very similar to the other one. I don't feel these questions are as advanced as the WJEC. P and S waves are detected. Which is detected first? The primary waves. The P waves. Explain your answer. Primary waves are faster. P waves are faster than secondary waves. We take some measurements. The exact position of the earthquake. How do they do this? Well, if you can measure the difference in time between the S and P waves, then you can figure out how far away from a secondary station. If you compare their delay to another station, you can figure out, if you know how far you could then figure out how far away that station is from the epicenter. And you've seen in the other question, if you get a little map, if you've got 2 circles intersecting, there's 1 or 2 places where they can intersect. So you kind of seen that diagram from the other question, haven't you? Just can you explain that? S waves do not travel through the Earth's inner core. Why not? S waves do not travel through liquid, and the inner core is liquid. Boom. Leave it like that. Okay, and S and P waves are different here. Good. Calculate the speed of the wave. Looks to me like a wavelength is going to be 0.8 meters because we've got two wavelengths in the 1.6. And this is the amplitude, so we're not worried about that. Well, that's double the amplitude. We're not worried about that. Here's the frequency. It'll be the 0.8 times 1.2, which is actually 0.96, isn't it? And what is the amplitude of the wave? Well, we just said the amplitude is going to be half of that, so I would say 0.11. Let's look at the mark scheme for this. P waves are faster, so they're there first, right? We measure the lag time, the delay time, and then we can determine the distance like that, okay? But difference in time can be used to calculate distance from earthquake. Okay, that gives you straight up two. This is one each, that's fine. Find time taken by waves, determine idea of triangulating waves. Yeah, okay, you just say I'm going to triangulate. Hope you know what that means. It doesn't matter, does it? Compare results from different. Now that's kind of what all we were saying. They can't get through because it's liquid, right? Oh, what's this? Ignore S waves can't get through liquid. S waves can't get through inner core 0. Oh, they're being a little picky. S waves do not travel through the Earth's inner core. Explain why. Oh, interesting. Because the outer core is liquid. Ignore S waves can't get through liquid. Oh, I guess if you say that, you are implying the inner core is liquid. They can't even get to the inner core because the outer core is liquid. Ooh, that's an interesting little twist. Be mindful of that, ladies and gentlemen. Okay, so we got the 0.96. It's if answer is incomplete, you get a mark for showing your work. Okay, and then 0.11 we said also. Right, that takes us up to the end. Do continue practicing. Do continue with your written answers. Take a look at as many of your specific questions as possible, whether it be seismic waves in the fiber optics versus satellite communication. Make sure that you've practiced as many of those questions as you can get your hands on for your particular exam board questions. This goes the same thing for the AQA questions on how your eye works and lenses that we saw in part 1 of our 2-part series here. Okay. And then also make sure, like for the real basic stuff like wave properties, TIR, that sort of thing, these calculations, feel free to look at questions from all different exam boards so you get a real good spread of the type of things that they'll be asking you, all right? And the more experience you have and the more practice you've done, this should be a fairly straightforward and easy unit for you if you've done your practice. Okay, happy revising, thanks for watching, and we'll see you next time.